Hi, welcome back. In this video, we're just going to define the kernel and the range of a linear transformation, and then we'll learn some properties and do a couple of quick examples. So let's start with the kernel. The kernel of a linear transformation is also called the null space of the transformation. So suppose we have a linear transformation from V to W. The kernel of T is defined to be the set of all vectors in V such that T of V is equal to the zero vector, and that's the zero vector in W. All right, let's look at a quick example. Suppose we have this linear transformation from the vector space of all polynomials of degree at most 3 to the vector space of all 2 by 2 matrices, and it's defined in this way. T of the third degree polynomial with coefficients a0, a1, a2, a3 is equal to this 2 by 2 matrix. All right, so we're going to find the kernel of this transformation. So if we take any polynomial, let's say it's c0 plus c1x plus c2x squared plus c3x to the third, and it's in the kernel of T, that means that T of this polynomial, so the 2 by 2 matrix, c0 plus c1, 0, 0, c2 plus c3, so this is T of this polynomial. That's got to be equal to the 2 by 2 zero matrix. That's the zero vector in M22. And that means that C0 plus C1 is 0 and C2 plus C3 is 0. So we get the two equations, C1 equals negative C0 and C3 equals negative C2. So we have two free variables, C0 and C2, so we can let C0 be the parameter S, and C2 is the parameter T, and we can rewrite the polynomial P of x to be S minus S times x plus T times x squared minus T times x to the third. And then we can rewrite this polynomial as a linear combination of two polynomials. So we can write it as S times the polynomial 1 minus x plus T times the polynomial x squared minus x to the third. And we now have a basis for the kernel. So the kernel of the transformation T is the span of the two polynomials 1 minus x and x squared minus x to the third. All right, let's look at our first theorem. So theorem 6.3 tells us that the kernel of a linear transformation is actually a subspace of the vector space V. And let's just remind ourselves how to prove something is a subspace. So first of all, we have to prove that it's non-empty. What that means is we have to exhibit something that we know has to be in that set. So since we know that T of the zero vector in V has to be equal to the zero vector in W, that's one of the properties of linear transformations, that tells us that the zero vector in V is in the kernel of the linear transformation. So it's non-empty. Also, we have to show that it's closed under vector addition. So closure under addition, we take two things that we know are in the kernel. So let's say U and V are in the kernel of T. And then that means that T of U is the zero vector and T of V is also the zero vector in W. That means that if we take T of the sum, U plus V, using the properties of linear transformations, we know that linear transformations preserve addition, so that's got to be equal to T of U plus T of V. And we know that that's just 0 plus 0, and we know that this has to be the zero vector. So it's closed under addition. Let's look at closure under scalar multiplication. So let's take a vector u that we know is in the kernel, and let's take any scalar c. So that means that t of c times u, because it's a linear transformation, that's got to be c times t of u, because we know linear transformations preserve scalar multiplication. Well, t of u is 0, and we know that a scalar times 0 is just the 0 vector. So it's closed under scalar multiplication. So the kernel of any linear transformation is always a subspace of the domain of the linear transformation. And an easy corollary of this theorem says that if you happen to have a linear transformation from Rn to Rm, and it's defined by a matrix, multiplication by a matrix A, where A is an m by n matrix, that linear transformation, the kernel of it, is just the null space of the matrix. So the kernel of a linear transformation defined by a matrix is just the null space of the matrix. And that's why we can use the word null space when we're talking about the kernel of a linear transformation. So let's now turn our attention to the range of a linear transformation. Remember, the range is the set of all vectors w such that w is equal to t of v, or some v in the vector space v. All right, let's look at our first theorem about the range of a linear transformation. Theorem 6.4 tells us that the range of any linear transformation is also a subspace. It's a subspace of the vector space W. That means that it's non-empty. So remember, W is a vector space, so it contains an additive identity, or a zero vector. And we also know that T of the additive identity in V has to be equal to the additive identity in W. So the zero vector in W is in the range of the linear transformation because it's the image of the zero vector in V. So it's non-empty. And then using the properties of linear transformations, the property that it preserves vector addition and it preserves scalar multiplication, you can prove that the range is closed under vector addition and closed under scalar multiplication. So we're not going to go through the proof, but this theorem has a nice corollary about linear transformations that are defined by matrices. So if you happen to have a linear transformation from Rn to Rm that is defined by multiplication by an m by n matrix A, then the range of the transformation, T, is actually equal to the column space of A. And remember how we write the column space of a matrix. We write R of A. So R of A is the column space of the matrix A. And it's also the same as the range of the transformation defined by A. Let's look at another example. In this example, we're given a linear transformation from R3 to R2, and it's defined by multiplication by this 2 by 3 matrix A. And we're asked to find the basis for the range of T and a basis for the kernel of T. So let's look at part A. A basis for the range of T is just going to be a basis for the column space of the matrix A. So if we take A and do a couple of steps of Gauss-Jordan elimination, we get the reduced row echelon form of A, this 2 by 3 matrix in reduced row echelon form. And we can see that the first two columns of this matrix, the first two columns are linearly independent. That means that the first two columns of A, C1 and C2, form a basis for the column space of A. And so that means that a basis for the range of T is the set consisting of those the first two columns of A. Notice now that we have a set containing two vectors in a two-dimensional vector space, right? In R2, when you have a set of two linearly independent vectors, that is a basis for that vector space. So that's a basis for R2. So that means the range of T is all of R2. So let's now find a basis for the kernel of T. So if x is in the kernel of T, that means T of x is equal to 0. So x is in R3. It's in a three-dimensional vector space, but it gets mapped to the 0 vector in R2. So that means multiplication by A, multiply this vector in R3 by the matrix A, we're going to get the matrix, 0 matrix in R2, right? So we want to figure out what x1, x2, x3 have to be. Well, we can use the reduced row echelon form of A to get these two equations. x1 plus 2x3 has to be 0, and x2 plus 1/2 x3 has to be 0. We have one free variable, so x1 is negative 2x3, x2 is negative 1/2 x3. So x3 can be our parameter s, and we can write down the vector as s times negative 2, negative 1/2, 1, and that means that our basis for the kernel of the transformation consists of this one vector, negative 2, negative 1/2, 1. All right, in the next video, we'll talk about linear transformations that are one-to-one or onto, and I'll see you there.